Hey everyone, this is an interesting recording. It should be one of the slightly shorter versions. It's a nice recording. It's actually an example that I've been teaching for a long time, but I haven't really gotten around a chance to doing a recording, so I thought it would be a good time. About a year ago, so a year before this was actually recorded, I did a walkthrough, not so much of the math of what was happening or of the code, but rather just the forms of how the structures were fitting together. I think that's kind of useful to think about. You'll see some notes in this example along those lines. We're using the same example from a year ago. That is this Andrew Trask's work from 2015. And I really like this example because he has he's given us a Numpy example that is bare bones. Now, I'm not encouraging you to write your own neural net from a bare bones example of Numpy. In fact, that would be a bad idea. There's lots of implementation that's not here that's required for code to run correctly. But in terms of understanding how the baseline algorithm works, it's a really nice teaching example. So we're going to get started, as I almost always do, using Numpy to kick us off. And we're going to be looking at this data set X. And X is kind of interesting. Excuse me, wrong X. Clear that. Let's use our X here. Our X here is 4 rows of data with 3 columns each. Each column in this case corresponds to a feature that we don't really know what it is. And you can see here that I've put in comments to correspond to what the labels are. So the first row generates a label of 0, and the second row generates a label of 1, and then 0 as well. And I encourage you to take a moment, pause the video. I'll slow down talking for a sec so you can find the pause button, and just try to note what's interesting about the structure of our columns and how they correspond to our actual labels. And what you first might have noticed, perhaps the easiest to identify, is something curious about the third row, right? The third column. Our third column is all ones. That is, there's no correlation between column 3 and our labels. Right? Regardless of whether we generate a 0 or a 1, we're always giving a value of 1. So we effectively can remove that from thinking about. The second thing you might have noticed is that each column, each value is 0. So 0 generates a 0, and 0 generates a 1 from the first column. 1 generates a 1, and 1 generates a 0 from the first column. So there doesn't seem to be any correlation between those. And similarly, in the second column, a 0 generates a 0, and a 0 generates a 1. A 1 generates a 1, and a 1 generates a 0. Again, the second column has no correlation. That would be the second thing you might have noticed. The third thing, if you really paused and looked carefully, or if you'd seen this example before, you'd note that in fact, really what we're doing is we're looking for similarities. When it's 0 and 0, we generate a 0. When it's 1 and 1, we generate a 0. So when the types are the same, they generate a 0, and when one is true and the other is false, 0 or 1, 1 or 0, then we generate a 1. This is referred to as the XOR problem, and it's sort of a classic in terms of this space, but it may not be something you've seen if you weren't sort of formally trained. And what I've done is I've generated a Y value here that's in fact that same value. So why does this matter? Why is this useful? It's useful because in this case, there is no way to move from column 1 to our labels, nor is there any way to move from column 2 to our labels. We can only look at column 1 and column 2 together to understand how we have to generate our labels. All right, we always talk about feature interaction, and those feature interactions are important. This is the feature interaction that we're talking about. They either need to both be on or both be off to generate a 0. And if one is on or the other is on, you'll generate a 1. Okay, so now we're going to move to the neural net part. Again, going pretty fast. We're just trying to understand kind of high level what's happening. We're going to initialize 2 sets of synapses, synapse 0, and we're going to initialize synapse 1. Now these correspond to the random weights when you assign new layers of neural nets, and this is a tip that we're going to be using a 2-layer neural net rather than a deeper neural network. So it's very shallow, but we're starting with these values that are purely random. And if we looked at synapse 0, we would see that it is in fact a 3x4 matrix. And you see here I note the dimensions of the matrix just to be helpful. And if we looked at synapse 1, we'd see that it's a 4x1 matrix. So what we're effectively going to do is we're going to be taking our 4x3 matrix, multiplying it by a 3x4 matrix to generate a 4x4 matrix, take that 4x4 matrix and multiply it by a 4x1 matrix. The outcome, after we've gone through our synapse 0, our final multiplication, is we will have our labels. So what we have here, now we move on to the training phase. These would be the equivalent of like our epochs. We're using 6,000, a very large number, and we don't have to actually run this in the loop because the loop really isn't necessary. This J variable is never used. We're going to just focus on this first pass, and we'll execute. And what do we notice about the first pass? Well, the first thing we might notice is that we're taking the dot product of x, that's our original data, and multiplying against this synapse 0, which was randomly assigned. And we get out a matrix that looks like this. This is the hard part of understanding what's going on inside a neural net. How can you sort of understand? And this is, again, like I said, a 4x4 matrix. And now we'll take the second object, the object that came out, the 4x4, and then we'll do again a dot product, but now with synapse 1. And we'll end up with an L2 matrix. And if we do L2.shape, we can see this is a 4x1 matrix. This corresponds to our best guess. Now I skipped over part of the math. I skipped over the math that's everything outside of that one dot product, but the reason I did that is that this is a sigmoid activation function. So we'll talk about the nonlinearity, a dot product wrapped with some nonlinearity. We do a matrix multiplication, add a non-layer component, get an output, feed it back in, do a matrix multiplication, add a nonlinear output, we get a set of values. Now, what we'd like to do is we'd like to see how close this is. If we picked by chance alone the perfect values for synth 0 and synth 1, very unlikely, very, very unlikely, we would see that L2 had the correct labels. It would have a 0, 1, 1, 0 as the output. But of course, we don't get anything like that. We output our potential labels, and we see we have a value of 0.49, 0.41, 0.45, 0.37. This doesn't look anything like we'd want. We would like it to be 0, 1, 1. So what do we need to do? We need to compute the error. And what are we going to do? We're going to generate that by looking at the gradient. That is the direction we need to go. Now, the reason we chose a sigmoid, and the reason sigmoid was one of the first approaches really for neural nets, was because we have this closed form solution for calculating the gradient. We don't have to sample. We can just compute it. That's worth spending some time if you're interested in looking it up. But for our purposes, we're not going to focus on that. We're just going to be looking at how this functions. And if we look at that L2 delta, what do we see? We see that the direction that we need to go is our first value needs to go down. Right? We needed a 0, 1, 1, 0. We need our second and third value to go up. They need to rise. And our fourth value also needs to go down. And if we look at our predictions, it's giving us a sense of how much we need to push down this value. Right? Needs to go down more than this value. This value only needs to go down a little bit less. That's closer to 0, 0.37 is. And so now we can say, now that we've figured out the direction that L2 needs to go, we need to compute the direction that the weights in level 1 need to go as well for synth 1, layer 1 I should say, not level. And once we've calculated the L1 delta, but let's just look at that to see it makes absolutely no sense. It's very confusing to try to understand. We'll go back and we'll update the synapse 1, and we'll update the synapse 0 with these two L1 and L2 deltas. And now we're ready. We've performed a single epoch, so 1 of 6,000 in our original code, and we're ready to run this again. So let's check and see how much progress we've made. L2, in fact, doesn't seem to have made much progress at all, right? A very small movement. And what we can do here, in fact, is let's just run this a few times. And then we'll check our L2 again, and we see that our L2 is moving, but it doesn't seem to be moving in any direction that we really recognize as being valuable. So we run it a few more times. We check, and again, it doesn't seem to be working. Right? We needed a 0, 1, 1, 0, and instead we've got a number that's above the 0.5, below, above, below. It doesn't seem to looking very good, right? We'd wonder if we're actually learning. And so now what we can do is, instead of doing this, iteration by iteration, we can throw another 6,000 epochs at it. And now we can look at our L2 delta, or our L2, and we see that our L2 is in fact starting to look exactly like what we wanted, a value of 0, a value of 0 on the first and last, and a value of 1 in the center. And if we wanted to, we could run this a couple more times. We could run it again and check our L2. And we see that, in fact, we were getting closer and closer to that 0 and 1. It's immaterial at this point. We can make our decision. We can see clearly that our algorithm has latched onto the signal that's required. Now, it's worth pointing out, we've run 6,000 iterations to be able to identify a four-row data set. So a single, very straightforward nonlinearity still required a large number. So this isn't a very efficient approach in terms of computation, in terms of what we've done, but it does point us in the right direction. It helps us understand the structure of how neural nets work at a low level. Andrew has a new book actually out that I haven't had a chance to look at, but I think I've just got a copy of one that's coming. And so I'm going to have a chance to look at it. I'm hoping that actually it will serve as a good example for us to use going forward for more examples of very easily to hold neural nets that you can sort of touch and feel and not have them be abstracted and hidden inside an architecture, but rather placed and made very plain. Because I do think that's very helpful to make some of these pieces a little cleaner and simpler to work with. Anyway, thanks so much for watching, and speak with you soon.